We're going to hear from Zoe de Beurs from the University of Texas at Austin, who will tell us about classifying X-ray binaries.
Let me just check. Does this? Oh, yes, thank you.
Yes, you're definitely on.
The mic works? Okay, perfect. Yes, so as Matt said, I'm a rising fourth year at the University of Texas at Austin, studying physics and astronomy there. And this summer, I had the opportunity to work here at the CFA with Dr. Saku Vertlek and Nazma Islam on developing a novel tool for classifying the compact objects in X-ray binaries using 3 machine learning methods. So first off, what are X-ray binaries exactly? So X-ray binaries consist of a compact object together with a main sequence or supergiant companion star, and they're orbiting their common center of mass. So this compact object, which we have here in the center, can be a black hole, a pulsing neutron star, or a non-pulsing neutron star, or a white dwarf. In this study, we focus on the first 3 because our instrument isn't sensitive to those that have white dwarfs as their compact objects. And so X-ray binaries are some of the brightest sources that we can see in the X-ray sky, and that's because they manifest themselves through an accretion process where you have accretion onto the compact object from the companion star. And so this accretion process releases energy over nearly the entire electromagnetic spectrum, but it peaks in the X-ray. And this can give us time-variant information that allows us to constrain what kind of system we might be looking at. And we also can look at the features of X-ray binaries to categorize them into distinct subcategories depending on the presence of the magnetic fields, the mass of the companion star, like I said, the identity of the compact object, the spectral characteristics, how maybe the luminosity varies, the presence or absence of jets that we can see here, and as well as the strength of the magnetic field. So here I have a visualization of what one of these X-ray binaries might look like. So let's go. So this is a black hole X-ray binary, GROJ 165549, and here you can see how it's orbiting its common center of mass, and it's accreting mass from this giant blue companion star, which is going onto the accretion disk here in red, and then eventually it goes past the event horizon. And so this is kind of an artist's conception of what it would look like. This isn't necessarily what we as astronomers usually look like when we're actually trying to analyze X-ray binaries. Instead, we might look at light curves. So these are going to be the average number of counts in X-rays of the number of photons and then they're going to be over the course of 15 years for these specific cases. So this is ASM RCE data. And so when you look at these spectra, you might wonder, am I looking at an X-ray binary where the compact object is a black hole or a neutron star? And your guess is as good as mine, because you're probably going to be wrong when you look at these. You might think, okay, these two look very similar, and these two look very similar. So maybe the one on the left is a black hole, maybe the one on the right is a neutron star. That's not true. Actually, what's the case instead is that the ones on the top here are both black holes. The ones on the bottom here are both neutron stars. And so just looking at light curves, we usually can't necessarily tell whether what kind of a compact object we're actually looking at. Instead, people usually look at color intensity and color diagrams, and I'll be talking more about those in a minute. But first off, this kind of indicates to you that we also need a straightforward method of classification. So some X-ray binaries have been observed for over half a century, but we still fail to classify them in some of these cases. And with the size of data sets ever increasing through large surveys such as ASM and MAXI, as well as missions that look at extragalactic sources, such as Chandra, we enter the big data era of X-ray astronomy, and it becomes increasingly important to have a straightforward, efficient method for classification. It's especially important because currently these methods that we use are often limited to bright objects, requiring extensive monitoring and various ground-based telescopes. So we want an easy means of classification for these X-ray binaries. So we have one problem that we sought to tackle with 3 different methods. So we're using a Bayesian Gaussian process model, a KNearest Neighbors model, and support vector machines. And so these are 3 common machine learning methods that are often used for classification that we wanted to compare. But first off, what does our data actually look like, and how do we use this? So like I said, people often use color, or color intensity diagrams. So what do I mean when I say color? So X-ray colors are defined as the ratio of counts in different energy bands. So when I'm talking about the hard colors, I'm talking about the number of counts in a higher energy band divided by the number of counts in a medium range energy band. Whereas with the soft colors, I'm talking about the number of counts in a lower energy band divided by those in a medium energy band. So when we're looking at X-ray binaries, we might see that in different stages of their lifetime, they might be occupying a region more towards the bottom or more towards the right, and they might be more in a hard state or a soft state. So what do these sources actually look like? So if we look at black holes, they're occupying this region, and so these are our sources, and there's 10 different ones of them. When we add our non-pulsing neutron stars, we see that they occupy a very similar region within this color-color diagram. Lastly, when we add our pulsars, we see that they are spatially somewhat distinct, but there's a lot of overlap within this diagram as to where these different sources are. So we see that these two-dimensional representations of our data obscure the geometric separation that actually exists between these classes. If we instead have the intensity on the y-axis, we see a very similar pattern that we can't necessarily discriminate between sources with these two-dimensional diagrams. So instead we move to color-color intensity diagrams, which are three-dimensional representations of our data. And so what we see here is in purple you have our black hole sources, in orange our non-pulsing neutron stars, and in green our pulsars. And so we can see that we can actually spatially resolve these different classes using these three-dimensional diagrams. So what do we actually do with this data? And how do we actually develop a model? So when we have one of these data points, what we do is we can create an n by 3 matrix where each row corresponds to a single point. So each row might be the value for the soft color, the value for the hard color, and the relative intensity for a single point. That is then mapped to a classification of 1, 2, or 3, where that can be a black hole, a non-pulsing neutron star, or a pulsar. So where do we actually get this data from? So we're using data from the Monitor of All Sky X-ray image, MAXI, which is aboard the International Space Station and has been in operation since 2009. And in this way, it was one of the first astronomical missions to be aboard the International Space Station. Currently, it has the highest resolution among all current X-ray all-sky monitors and operates at the energy range from 2 to 30 kiloelectron volts. So from MAXI, we took 21 different sources that are well established and have well-established classifications that we already know, and that was our training set. You might look at this and think 21 sources and you're doing machine learning. That's kind of insane. Usually machine learning methods use thousands of examples, but you might be surprised to see that it actually works quite well for classification. So once we have our training set of 21 sources, we use something called k-fold cross-validation. And what that means is we have our 21 sources, we remove 2 of them, and then we train on the remaining 19, and then ask the model to predict the classification for the other 2. Then we put those 2 back into the training set, randomly choose 2 other sources, and keep on iterating through this process until we validated every single source and gotten a classification for it. Lastly, for our testing set, we're looking at sources that have somewhat ambiguous classifications. In some of the other methods that have been used in the past, we do know what their classification should be, but we've seen that some of these machine learning methods that have been used before can't output the correct classification, and so we're curious to see how our methods compare to this. So what methods are we exactly using for this? So we're first off using a Bayesian Gaussian process model. So Gaussian processes are a powerful tool for classification. Their greatest practical advantage is they can give a reliable estimate of the uncertainty within the model. And the term Bayesian just refers to the fact that the probability distribution for each output of certain predictions can be updated based on new incoming training data or new priors. So I'm going to be talking about a specific example just to illustrate how this actually works. So many of you might have been able to attend last week's colloquium by Jonathan about the history of all the Apollo missions. And so the question we're going to seek to answer is, what is Jonathan McDowell's favorite Apollo mission using this Gaussian process? So let's say that we know of Jonathan, but maybe we don't know him very well personally. And so our Gaussian process might look something like this, where these are our different Apollo missions, and then on the y-axis you have the probability that that might be his favorite. And so This Gaussian process is essentially a distribution over all the possible functions that might fit this. And so each of the colored lines corresponds to a sample of the possible distributions that may fit this problem. Assuming we have no prior beliefs about what Jonathan's favorite mission is, our best guess for our mean is some middle at 0, and we can see that we have all these different functions that could possibly fit it because we really have no idea what the answer might be before his talk started. But as Jonathan's talk progresses, he briefly talks about Apollo 1 mission, and stresses the importance of Apollo 8, since this was the first time humans left the gravitational sphere of influence, and it was the first time humans orbited the moon. So since he didn't talk that long about Apollo 1, we assume it might be somewhat important, but not super important. Apollo 8 he talked about for quite a while, and since it's historically important, we might assign it a probability of 2, where we range from -3 to 3. But we still see that we have quite a bit of possible functions that could fit this, even though our Gaussian process is more constrained now. So next, towards the end of the talk, we counted that Jonathan spent 24 slides on Apollo 11. So this may mean that it has a relatively high probability of being his favorite. However, we also realize that Jonathan may be very good at actually tailoring his talk to his audience and knows that many people will be curious about Apollo 11. So in the end, we assume that it actually has quite a low probability of being it, but higher than some of the other missions. Then we also notice the fact that he does not mention Apollo 2 through 7, so those probably have quite a low probability of actually being his favorite as well. After the talk, we might actually ask Jonathan if he could have talked about any other missions for longer, which one would it be? And he starts talking about Apollo 15 and about its use of the rover, as well as the spectacular selenology of the Hadley Delta. And so we assume that the highest probability might be for Apollo 15, and we use a Bayesian Gaussian process to predict his favorite Apollo mission. Yes. Which is true, right, Jonathan?
Yes, I think 8 and 15 are definitely.
Yes.
Although I do have a sneaking appreciation for 5, just because I like really obscure missions.
Yes, so that means that maybe some of our priors for Apollo 5 might have not been as accurate. But yes, so this is kind of an illustration of how a Bayesian Gaussian process can be adjusted with different training data that we may input. And so the next method that I'm going to be describing is a simpler algorithm called KNearest Neighbors. It uses a very straightforward, clear-cut decision rule, but essentially what it does is it's really well illustrated with a two-dimensional example. So say we have our black holes in purple here and our neutron stars on the bottom. And we have this input point, which is your question mark, and we don't know what the classification should be. So what the model will do is it'll use your regular distance formula, and it'll calculate the distance from this one point to every single other point in your data set. And then say that I want to look at the 5 nearest neighbors, so k is equal to 5, then I will see that 3 out of 5 are neutron stars, 2 out of 5 are black holes, so the probability of being a neutron star for this point is 60%, and for a black hole is 40%. And so that's how this algorithm works. And we just wanted to see, since we do see clustering of our data, whether this would be a good predictive algorithm. The last algorithm we use is support vector machines. So it could be a promising way to classify these X-ray binaries because it uses complex hyperplanes. And so what that means is in a support vector machine, given the input and output data for each source, the goal is to find the largest separation between the data. So over here you have another two-dimensional simple example where you have your black holes and your neutron stars that are linearly separable. So what the algorithm will do is it'll find the distance between the closest 2 points, and then the medium between them will be your actually separator line. So if you have a new input data point, it'll be classified based on where it lies with relation to this line. It has the obvious problem that if your data isn't linearly separable, this won't do very well. So instead we use something called the kernel trick, which I can explain later if people are curious, but essentially what it allows you to do is to project your points into a higher dimensional space, allowing you to have a non-linear separator line. So how do all of these algorithms actually do? So when we look at our predictions for the validation of the black hole classes, where all the purple ones are going to be the highest probability to be a black hole, we have our support vector machines probability, our KNN probability, and our Bayesian Gaussian process. And we see that, unfortunately, not all of them are being classified as black holes. We see that GRS 1915 as well as 4U 1630 are misclassified for both of these algorithms, but correctly classified for one of them for support vector machines. And you might wonder, why could this be? So we can look at the actual color intensity diagrams where we plot all the non-pulsing neutron star sources together with our GRS 1915, which is misclassified, as well as the black hole sources with GRS 1915. So what we can see in the bottom one is that the training data for this specific source doesn't necessarily overlap as much with GRS 1915. So it traces quite a unique pattern out in the color intensity diagram, which is not uncommon for X-ray binaries, as they can be quite unique in their signatures. It has a little bit more spatial overlap with the non-pulsing neutron star, and so the model outputs that as the correct prediction. What we do see is that the Bayesian Gaussian process does a little better of indicating that maybe this is a black hole. Now, if we look at 4U1630, we see something similar, where it also traces kind of a unique pattern out in the color intensity diagram, and has some overlap with the black holes, but also some overlap with the non-pulsing neutron stars. So we see that support vector machines can output the correct prediction, but the other algorithms misclassify it. However, again, Bayesian Gaussian process gives a better estimate of the uncertainty that the algorithm doesn't exactly know what this might be, and so it's more ideal for that specific case. Now, for non-pulsing neutron stars, it looks great. We see that essentially it's being classified, it classifies all of them correctly as non-pulsing neutron stars, which is very promising, especially considering the fact that, again, we're only using 21 training examples instead of thousands or hundreds of thousands. For pulsars, we see that it also outputs the correct predictions for every single one of them. However, it's not perfect. For bursters, which are a special subclass of non-pulsing neutron stars, we see that they often tend to be misclassified as black holes. So why might this be? So when we actually plot all the black holes and the misclassified burster sources, we see that they again trace a unique pattern in the color intensity diagram, and they have quite a bit of spatial overlap with these non-pulsing neutron stars. And so it kind of makes sense that the training set might not be representative for these specific examples. And so overall, we find that the highest predictive accuracy is from the support vector machines and the KNearest neighbor models. However, the Bayesian Gaussian process gives a better estimate of the uncertainty in the prediction of the correct class and a better distribution. If we compare KNearest neighbors and support vector machines, we find that KNearest neighbors gives a better or more consistent prediction across different classes. So even though we can see that black holes do better for the support vector machines, non-pulsing neutron stars only have a 69% accuracy. And so if you're looking at data that has all three classes, this might be a superior model to use. Our overall conclusions are that the Bayesian Gaussian process works across different data sets, as had been done in 2015 using ASM data. We find that all models correctly classify most neutron star systems, but all models also tend to misclassify the burster systems. Overall, we find that there's a high predictive accuracy of these models for classifying most X-ray binary systems, paving the way for a feasible method for classifying X-ray binaries into pulsars, non-pulsing neutron stars, and black holes. I would like to thank Dr. Saku Vrtlek and Nazma Islam for their mentorship throughout the summer and just teaching me everything I know and making it just a very enjoyable summer. And Jonathan and Matt Ashby for welcoming us to Cambridge and just making it feel like we actually belong here. So, thank you.
Zoe.